Hello, good people. Welcome to this video. This video is aimed at doing a presentation of a project, capstone project that is based on deep learning. So this project is based on uh, providing a solution for image classification to images that are from MRI of the brain. So it is aimed on providing a model, machine learning model that will predict image into different categories. So the different categories of the images are brain tumor types, that is meningioma, glioma, pituitary, and we also have I also have tumors. I mean, the brain MRI images that are not tumor. So I want to show you the data set that we have here. From the data set, then we will begin the project by uploading the images, the data set into our working station, that is Jupyter Notebook. I'll use Visual Studio Code. Then after that, we will begin by data augmentation. Then we will do a model building. I will build a CNN, that is convolutional neural network. That is a custom CNN. Then I will train the 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 CNN on the train test train set data, and then I will evaluate it. After evaluation, I'll do prediction with the test set data. After that, build a I'll do much transfer learning where we'll see which one works best. After doing transfer learning, I'll save the model. Then the model will be deployed into a web application that is developed by Streamlit. That's the entire workflow of this project and this presentation. So I hope you stay with me as I begin. So I begin by showing the dataset here. You can see this is the data set. Or you can see it's a brain tumor MRI. It is stored in this particular folder here. This folder has three folders, that is this test set, train set, and validation set. So this is let me just open one of the folders, that is test set. We also have the four classes, that is for folders also glioma tumor. Let me just open glioma tumor that you may see the images there. These are the images there in for glioma tumor, brain type tumor, glioma. Let me also open meningioma. You see, these are the types here you see for meningioma images. Then let me open for no tumor. I'll do that because of time. I'll just show for no tumor. You see, these are the images for no tumor. So the summary of this particular data set is that we have a total of 2,444,000 images, and the images are as you can see in these folders, they're divided into test set, train set, and validation set. So this one was done by medical experts. They know the kind of tumor. So this particular project is very important because based on these tumors, we are gonna develop a model that will be used for model prediction, predicting of tumor types, which will help the specialists in hospitals to try to predict uh, tumors, and it also helps in doing research. So this project is very important. Uh, this particular project here is very important. So that's why I want to show you everything from the beginning. So one thing after that, after showing you the images, the data set, then I go directly to show you now the code of everything here. So this is the code actually. So the code of the project, it begins here. I hope you can see my screen here. So as I've just illustrated and told you, this project aims to develop a deep learning-based solution for classifying brain MRI tumor images into multiple categories according to tumor type. It involves building a custom model, CNN, custom convolutional neural network from scratch and enhancing performance through transfer learning using pre-trained model. Then I will deploy it in a user-friendly streaming web application to enable real-time tumor type prediction from uploaded MRI images. Yeah, so one will be able just to load the images into the app, and then the algorithm will do its best. Just upload, then you predict And you will see it's very fascinating that it predicts accurately. I have tried it. So the problem statement, okay, before that, this is the link to my project. It's in GitHub actually. So this is a link to my project. Oh, then, so as I begin the project, I have to load the data set. I mean, I have to import the necessary libraries. So, this one, CNN will be using PyTorch and Keras and all the other important required libraries. These are them here. They'll be required. So I do this code here is to definition and research transforming images. Then here I load the data set from the using the image folder function of the PyTorch library. Then this is now the root. This is the we call it where my data is. So this is where I get the data from. This is where we get our data from. It is the route to our data, the path to our data. So after that, after loading the data, then I want to confirm the classes. Where are they well loaded? Yes, we have glioma, meningioma, no tumor, pituitary, and they're indexing. The good thing with the PyTorch is that it automatically provides an numerical index. We know that machine learning cannot learn on text data. You must change it to numerical data. So it actually does that so well here. So that one will be so good for us. Then now we do what we load the data using the loader. So for us to view, we want to have the view of the data. So this function here is what will help us to see view the images that have been uploaded to this particular project now. So these are the images you can see the randomly from the different classes, glioma, no tumor, pituitary. You see these are them here. So I also done it precisely by doing defining another uh, function to to display the images with based with their classes. So like randomly, like now this one here, you see the images are displayed randomly. This is pituitary tumor, this is glioma, meningioma, glioma. So it didn't print out for no tumor. That's okay. The next thing is doing data augmentation. This is now where we apply, this is where we introduce diversity into our images because, images that we get from MRI might be are so different in nature. So we need to make our model to to be very generalized. We don't just have to train on just same data set. No. So in data augmentation, we introduce uh, diversity into our train set data set so that the machine learning model any should not overfit, but be able to generalize even with the new images that will be provided. So this is the code for data augmentation. We do transform, we zoom, we rotate the images so that the CNN algorithm can be able to get diversity on the images so that even if any other image that was not been trained on can be given, then there's a lot of diversity in the training set. So the algorithm will already know, will already have its size. So we also we do some random affine, we do some random rotation to the images, then we introduce some horizontal flip, we resize, then we do some brightness adjustments, so that we may introduce diversity to the data in the training set. So then here I print the augmented data. You see it has some kind of diversity. Like now this one here, you can see this image here is a little bit more brightened. And then we can see the kind of those that are flipped a little bit. So introduces diversity to the training set. Then we have here for label encoding and batching that I'd already explained, that the image folder of PyTorch takes control of that by actually assigning numbers to the classes. Now you see here, glioma is assigned to class to number 0, meningioma is assigned to 1, notioma is assigned to 2, and pituitary is assigned to 3. This will help in training the CNN algorithm. Then the next thing is to do the model building. So I build the CNN. So actually I build 3 layers, 3 convolutional layers. So this 3 convolutional layers is where the CNN will pass using the kernel of size 3 times 3. It will scan, then it will understand the pixels of the images, and then convolute them together at the uh, where at the last layer, that is fully connected layer. That's when learn the what you call it, we call it the pattern of the images. So this is the actually this is the build them RN the CNN architecture. So you use here ReLU activation function. Yeah, we use ReLU activation function to introduce um, nonlinearity to this convolutional neural network. So the next thing I do is instantiate the model here. See, this is the architecture of the model. You have 3 convolutional layers, then fully connected layer, then prediction layer, last one. And one important thing now here is training this. So this is what is so fascinating. I use E10 epoch, and now this is the date. This is the code for the training. And this after every epoch, you can see there is a, a output here for every epoch, how the model works, how it brings prediction. Actually, you can introduce some techniques like early stopping. Actually, I did introduce some early stoppings and then try to evaluate and saw how the model was performing. Before actually the 10 epochs were over, I introduced some early stopping, and I found that in the early stopping, the model does not perform very well. But after the 10 epochs are over, then when I evaluated it, I found that it performs very, very well. So this is the evaluation code here of the model. Then let's check how the model performs actually. So the confusion matrix produces intuitive illustration visualization of how the model performs. And you can see that precision, recall, and F1 score is quite promising, it's quite good, quite good for this particular custom CNN. You see that the model is able to identify 90% of the glioma tumor. It's also able to identify 83%. It's also able to identify 85% of no tumor and 96% on pituitary. It seems that that performs so well on uh, pituitary tumor types. See here on recall, the classes that have been marked as pituitary, it's able to identify them 100%. But for the predicted ones to be pituitary, actually 96% were predicted with precision. They were predicted with accuracy of 96% that yes, indeed, they were pituitary. So F1 score, we know, it's a measure evaluation matrix for, that combines precision and recall. And then this model has 0.89% accuracy on overall performance. Then we had a total of trainings of about this is the tests set of 246 total. So this model performs uh, very better, a little bit more, you can see. So let's visualize the confusion matrix. See, this is a visualization of the confusion matrix. You see the glioma performs best. And it's able to identify also pituitary, you see it performs best. But I think in meningioma and no tumor, maybe because of lack of more images, that is why, because you can see uh, actually meningioma has 63 and no tumor has 49. So there's lack of enough, there's imbalance of images from meningioma and no tumor. That's why it's maybe the algorithm is not performing so best. But I think in overall, the accuracy is wonderful. Then from that point on, I have this what I've just explained, the position. And the next thing is to do transfer learning, where I will upload, I will use a pre-trained model to do a fine-tuning so that it may be used to predict these images, these MRI brain images. I use RestNet, the pre-trained model that is RestNet, and I also use 10 epochs here, and it turned out that it works so well. Let us just go. This is the epochs, the pre-training. Let us see the evaluation of the model, how it performed well on this. Yeah, at least the precision, recall, and reference score of the meningioma, glioma, and tumor has increased. You see, here is around 86.5%, 93%, and 4. And transfunction based also on accuracy and all the other evaluation metrics. So this model, you can see observation glioma and pituitary outstanding performance, no tumor balanced position and record, and the glioma slightly slower record, but still strong. Conclusion, the model performs consistently across all classes, even considering class imbalance. So this is the code to save this particular model, which shall be used to build a Streamlit application app, which somebody can now load the images and then use it for prediction. So I just want to show you the Streamlit code to build the code. So first of all, I just I imported Streamlit as ST and then imported the other libraries PyTorch because required. And then define the structure of the model, the same as the training that we did there. And then I instantiated and loaded the weights. And then after that, I now built the UI. Let me just load it. Let me just run it. And let me run it, then you may see. Let me run it, stimulate. Brain tube, stimulate run, brain, tumor, stimulate up, let fewer. Wonderful. So it takes me to a different page that is, let me just go to that screen page. Oh, sorry for, yeah, so that's it, that's the screen actually. You see, so this is the web application where now you can actually now load any new feature, any new picture, image. Let me just load that image. I actually downloaded some image from the website, from the internet. Let me see if I can how it performed. So you see, I just downloaded some images from the internet. See how it do prediction upon. So prediction, see how does it predict. And it predicts that this particular image has no tumor. Let me try another image. Let's see how it performs. Upload another. You can browse. This one I downloaded from again from the internet. It is a meningioma actually. It's a meningioma scan. Let's see if it will be able to identify it as a meningioma tumor. So I don't know. It's uploaded the image here. So this is the one that I upload. I mean, this is the one that I downloaded from the internet. See, let's predict this image and see how does the method predicts it. Oh yeah, it predicts it as meningioma tumor. So this model performs very well with all the images that you upload here. It will correctly, at least, to correctly predict the image, which type of tumor it is, whether it has meningioma tumor, whether it's pituitary, or whether there's no tumor in that particular image. So that is how this particular model is performing. And so the importance of this particular project is that this project can be used by specialists, the radiologists, in diagnosing brain tumors. So specialists, they can just actually just if they have just done an MRI, then that they take that image, then they have just upload it here, and then they they just click predict here, and that image will be predicted whether it's which image. You must see how that is very important. So another thing that can be used is that this data set will also be used to develop new treatment for brain tumors. Yeah, so these are there are quite a number of application to this particular project. So I hope that is I hope this project you have gotten some understanding on the functioning of the CNN, plus how CNN works, and how the images have been uh, trained, how they are used for training the algorithm, and then how they are used for making prediction. So this is the project capstone project. So I think you have enjoyed the session. I have taken you through it, and thank you so much for staying. I hope we meet next again. I hope we meet next time again. We'll also do another project of particular type. So thank you. Thank you.